So I will be considering today a free collision of a sticky puck with a uniform rod. So the problem setup is the following. Let's assume that we have a uniform rod. It's got mass little m and length little l, and headed towards the uniform rod is a small puck, which we can assume to be a point mass in this case, and it's moving towards the rod with a initial velocity v0. So let's assume that it eventually is going to collide with the rod someplace here and make some angle theta in doing so and stick to it. It's a sticky puck, so it's going to stick to it, and our problem is to describe the subsequent motion after sticking. So here's the problem. And when I say describe subsequent motion, I mean more than just qualitative. Well, let's see what happens qualitatively. It sticks to that, and then presumably the whole thing will move as a unit in some direction. And it'll also be rotating like that because it's not hitting it exactly in the middle. If it hits in the middle, it will not rotate, but if it hits away from the center of the rod, it's also going to start rotating. So we're going to try to describe the subsequent motion of it in terms of those variables, the center of mass, speed, and the rotation about the new center of mass. Now, the new center of mass, let us indicate that location by some asterisks here. So we have to put some details into all these things. Let me call the distance from the top end to the new center of mass d, and I'm going to call this distance from here to here, from the new center of mass to the point where impact occurs, I'll call that r. You'll see why that's important. And I've not told you yet where this impact occurs, so my drawing makes it look like 1/3 L, so I'll go with that. Now I've taken the mass of the puck and the mass of the rod to be the same because I don't want to see any ugly mathematics, so hopefully that will suffice. And I'm taking a coordinate system here where it's traditional. The y-axis is going to be up, the x-axis is going to go to the right, and the z-axis is going to come out of the page. Now the first thing that you do is not conserve energy. So that's the first don't. So I'll write here, never conserve energy. The collision, and the last thing you want to conserve is energy in a collision, because all kinds of things happen in a collision. Noise, heat, sticky deformation. So there's going to be a lot of problems. So never conserve energy. In fact, at the end, we'll see energy is lost in this problem. The one thing we can conserve is linear momentum. Let's review under what conditions linear momentum can be conserved. The sum of the external forces have to be 0. Now we're going to assume that this is a smooth table, no friction, and no air resistance, so that's valid. Well, that'll give us the initial momentum equals the final momentum. Observe that this is a vector equation because linear momentum is a vector. So linear momentum is certainly conserved. What about angular momentum? Now there is gravity, but it acts into the page. So the torque due to gravity is going to be in the xy plane. But in the z direction, there is no torque. So the sum of the external torques in the z direction is 0. So that means the initial angular momentum in the z direction, remember L is the angular momentum, is equal to the final angular momentum in the z direction. So these are the conservation principles that we have to apply to solve this problem. Let's start with the linear momentum. that's theta there, so that is also theta here. Let's write down an expression for the initial velocity v naught using this theta. Remember, the y component is adjacent, so that's going to be, y component is going to be cosine, and the x component is sine. So that is the decomposition of the vector in this coordinate system. And to conserve linear momentum, all we have to do, let's call this equation 1, and we'll call this equation 2. To conserve linear momentum, the initial momentum is mv naught of just the puck, and the final momentum is the momentum of the combined object. So the total mass is going to be m plus m, or 2m, times the velocity of the center of mass. I'm going to henceforth denote the center of mass by the star symbol. So we already have a valuable piece of information, and that is the center of mass moves with half the velocity of the puck. So that's a valuable result in itself, so I'll box that, where the velocity of the puck is given by this expression. What about the angular momentum? Now this is the tricky part. We have to make sure that the angular momentum is conserved about the new axis of rotation, the future axis of rotation. To find that, we need to find out what this little r vector is, and to find that out, the best way to proceed is to find the new center of mass coordinate. Taking the top point as my reference, the center of mass can be found as follows. The distance d is the mass of the rod times the location of the center of mass of the rod. The rod is very symmetric, so the center of mass is going to be exactly in the middle, plus the mass of the puck times the location of the center of mass of the puck. Well, the puck is a point particle, so its center of mass is going to be wherever it sticks. And since I said it sticks at 1/3 L, it means that it's 2/3 L from the top. So that's going to be 2/3 L divided by the total mass, which is 2m. So this is just some fraction adding. Let's take m times L outside. Then I have to add, these are lowercase l's by the way. So I'll have to add 1/2 and 2/3 divided by 2 times m. So the m's cancel out. 6 is a common denominator here in the numerator, so I'm going to write this as 6, and this is going to be 3 plus 4 divided by 2 times script L, and that's equal to 7/12 L. That's a neat little result right there. Next, let's find out what r is, the magnitude of the vector that points from the new center of mass to where the puck is going to stick. Well, that is d minus L over 2, because you see that's d, and excuse me, it's the r vector goes from the center of mass to the point of contact, so it's going to be 2/3 L minus d. That's what it is. It's 2/3 L minus d. So let's find out what that is. It's 2/3 L minus 7/12 L, and that's going to be 8/12. If I multiply the numerator and denominator by 4, I get 8/12 minus 7/12 L, or 1/12 L. Okay, so that's the R. Now let's look at the next thing we do is find the angular momentum. So let me just write what I'm going to be doing. I'm going to be conserving the angular momentum in the z direction along the axis passing through the future center of mass, that point star. So let's write that expression. The initial angular momentum L sub I is going to be rp sine theta, because that's the angular momentum of a point particle. The r vector magnitude is 1/12 L. P is mv naught, and sine theta is what it is. Now I just want to make sure that's the angle I have here. The momentum vector is going to be like this, and the angle between the momentum vector and the r vector is indeed the same as theta. So that's good. The final angular momentum, LF, is along the z direction, is the moment of inertia of the system about the new center of mass times omega f. So the next big undertaking is to find the new moment of inertia. So let's do that. So the moment of inertia is comprised of two parts. One is the moment of inertia of the rod about the new axis, plus the moment of inertia of the puck about that new axis. The moment of inertia of a rod about its center of mass is a well-known result. It's 1/12 ml squared, but it's parallel axised by this distance. That distance is d minus L over 2. So this distance here is d minus L over 2. And so let's quickly figure out that distance. D minus L over 2 is 7/12 L, because that's what I have for D, minus L over 2, which I can write as 6/12 L. And it's 1/12 L. Amazing. It's the same as that distance from here to here is the same as the distance from here to here. Well, it could be a coincidence. So I'm going to use that as my parallel axis shift distance. So it's going to be m times (1/12 L squared). Now what about the puck? The puck is a point mass, so that's moment of inertia of the puck about the new center of mass is just m times little r squared, and little r is just 1/12 L again, so that's m times 1/12 L squared, because the puck is a point mass. So that's the total value. Let's try to quickly add the fractions here. I'm going to get 1/12 plus m over 144, m over 144, 2 times m over 144, that is. So that's going to be m over 72. It's 1 over 72 times ml squared. So 6 times 12 are 72, so that's going to be 672 plus 172 ml squared, and that's 772 ml squared. So that's the new moment of inertia. Now we can substitute this. Remember, equation 2 tells us that the initial equals final moment, angular momentum. So I can find from this omega f is going to be 1/12, that's the initial, L mv naught sine theta, divided by the moment of inertia, which is 772 m little l squared. I keep going back and forth between capital L and little l, so I'll correct it here. I want to reserve capital L for the angular momentum and little l for the length of the rod. That's the reason why. So let me cancel out some things here. Well, 12 6 of 72 again. So that's going to be 6/7 V naught over L sine theta. So we have the second result. The angular speed of the combined object about the new center of mass is going to be that. So this way we've completely described the problem. Now the last bit that remains is to show that energy is in fact lost, and that's actually a pretty nice calculation, so let's do that too. The energy of the system, the final kinetic energy, is going to be comprised of both translation and rotation of the combined object. So let's find that first. The final kinetic energy, sum of the final kinetic energy, is going to be 1/2 I star omega F squared plus 1/2 the total mass times the speed of the center of mass squared. So let's figure that out. It's 1/2 times the moment of inertia is 772 ml squared times the final angular speed is that, but you're going to square it, so it's 3649 V naught squared over L squared sine squared theta plus, here I have m times, well, V star, which is V naught over 2, and you're squaring it, so it's V naught squared over 4. Let's see what happens here. 36 2s are 72, 7 7s are 49, so that looks nice. It's 4 times 7, 28, so that's 128 m V naught squared. Observe this, the L squareds cancel out, sine squared theta plus m V naught squared over 4. The initial kinetic energy is just 1/2 mv squared because the puck was the only one contributing to the initial kinetic energy. So now the question is 1/2 bigger than that? Let's ask that question. So that's the burning question. Is 1/2 bigger than 128 sine squared theta plus 1/4? If I subtract 1/4 from both sides, that's equivalent to asking the question, is 1/4 bigger than 128 sine squared theta? Let me multiply both sides by 28. So that statement is the same as asking if 7 is bigger than sine squared theta. And it is, because sine squared theta can never be bigger than 1. So energy is lost.